Okay, so this is where we stop. So concrete under tension is ignored because it is assumed that the tension is assumed to be carried entirely by reinforcement. And the reason being that the tensile strength of concrete is much lesser than its compressive strength. Therefore, and also the extent of cracking is not certain. As in some locations, they'll be cracking at say up to this depth. In other locations, the cracking might be up to this depth. So we don't know how much concrete is already cracked. So the extent of cracking is not certain. Therefore, we simply say that we consider concrete only above neutral axis. Whatever is below neutral axis, it is just for holding the reinforcement in position, resisting shear and so on. But we do not consider its contribution in flexion. Then the next assumption is that the distribution of compressive stress in concrete across the section is defined by idealized stress strain curve of concrete. Now, this might seem very complicated, but it's very easy. What this assumption says is that so if this is my section, I know that this is my strain variation. Now, I'm already aware of the stress strain graph of concrete. So this is a stress strain curve. Wherein here we have stress, here we have strain. So if I have to correlate this stress strain curve with this strain variation, what I will see is that the stress in concrete would be something like this. Parabolic up to here and then linear. It is what this assumption says. Right? So as the strain increases, the stress increases parabolically up to a certain point and then it is linear. So this is what this assumption says. And the last, I believe the last assumption is, okay, the second last assumption is that this design stress and steel reinforcement is obtained from the stress strain curve. Similarly, what the assumption says is that if there's a certain value of strain here, we will get the stress value by considering its stress strain curve. Okay, so whatever, so this is our stress, this is our strain. Whatever is the value of strain, we can get the corresponding value of stress using the idealized stress strain curve. Now the idealized, this is our original curve. The idealized curve looks something like this, or something like this. So if there's a certain value of strain, we can easily find out the value of stress from this particular curve. That's what the assumption says. And the last assumption is that there's a perfect bond between steel and concrete. The reason why we've made this assumption is because both, these are two different materials. These two different materials can act as a single material only when there's a transfer of strain from one material to another, or there's a transfer of stress from one material to another. And when will there be a transfer of strain or stress? When there's a bond between these. I think we briefly discussed what bond is and the importance of bond in transferring strain between steel and concrete. So this is just, just keep this assumption at the back of your mind. There has to be a good bond between the two materials so that they can transfer their strains to each other. So these are all the fundamental assumptions that we are going to make. And these are the assumptions that we also made before while learning the flexure for homogeneous materials. I believe you might have learned this in theory of structures 2, 3 somewhere then when you were studying structural mechanics or but I'm not sure what the name of the course is, but we called it strength of material or structural mechanics. Anyway, so this was the easier part. Now, while learning any element, like we followed this procedure in structural steel, that while learning any element, what we did is we first tried to find out what are the various modes of failure, or what are the various ways in which the element can fail, and then we sort of looked at various ways of making sure that we do not reach this kind of a failure. Okay, we're going to follow the same strategy here, wherein there are certain modes of failure, and we'll just make sure that these modes of failure do not occur, or if at all there's a failure, then we want a certain kind of a failure to happen. Now, you'll definitely understand by the end of this lecture what I mean by this. So the various modes of failure in a flexural member are, the various types of sections are a balanced section, an under reinforced section, and an over reinforced section. Now, when one reads this, there's a balanced section and there is an under reinforced section and over reinforced section. So you might intuitively feel that a balanced section is a perfect section. It is a balanced one. Then an under reinforced section might be a section wherein you are putting lesser reinforcement. Therefore, it is called as under reinforced section. And an over reinforced section might be a section wherein you are providing more reinforcement. Therefore, it is called as over reinforced section. So the first thing is, it is not what it means. Okay, now let us try to understand what this means. Now, I'm just going to read out this text, and then with the help of sketches, I'm going to explain what this means. Okay, so just I suggest that you read this text along with me. So, a section in which the area of tension steel, which means AST. Okay, area of tension steel is denoted by AST. S stands for steel, T stands for tension. So, a section in which the area of tension steel is such that at the ultimate limit state. Okay, what is the ultimate limit state? Ultimate limit state is a theoretical failure point. Beyond this, we consider the section to have failed. It is not functional anymore. Okay, so a section in which the area of tension steel is such that at the ultimate limit state, the compressive strain in the extreme fiber of concrete reaches ultimate strain. Now, what does that mean? This means at the ultimate limit strain, the strain here is 0.0035. Okay, so this is our balance neutral axis, or this is a neutral axis. This is concrete in compression. Below this is tension. Therefore, what it says is at the ultimate limit state, the compressive strain in the extreme fiber. So this is our extreme fiber of concrete reaches the ultimate strain. So our ultimate strain is 0.0035. And the tensile strain in steel reaches yield strain is termed as a balance section. So very simple. We are defining this in terms of strains. So at the ultimate limit state, if this value epsilon Cu is 0.0035 and epsilon Sy. Now, I just want you to intuitively understand what these uh, suffixes mean. So Sy is steel and it's yielding. And epsilon Cu is ultimate. U stands for ultimate and C stands for concrete. So this value is 0.0035 and this value is 0. 0.002 plus 0.87 Fy by ES. Such a section is called as a balance section. So both of these things are occurring at the same time. Just try to draw this. Okay, so if this is our section, this is our strain variation. This is our strain variation. This is the neutral axis. The depth of neutral axis is denoted by XU. Okay, where X is the distance and U stands for ultimate. So the depth of neutral axis is denoted by XU. So what this assumption says is that at the ultimate limit state, the strain here is 0.0035 and the strain here is 0.002 plus 0.87 Fy upon Es. So both these strain values occur at the same time. So we are reaching the maximum strain in concrete and the minimum strain in steel at the same time. Such a section is called as a balance section. Any questions here?
So does this mean that the value of epsilon sy is equal to 0.0035?
Could you please repeat?
Does this mean that the value of epsilon sy is equal to 0.0035?
Epsilon sy.
So, like this 0.002 plus 0.87y.
No. Okay. So this, that might happen when your xu is exactly equal to d by 2. I sort of understood your question, and I appreciate you asking this. So that will happen when this distance is equal to this distance. Okay, only then these triangles are similar and this value will be equal to this value. Okay, but in most cases, now this is a very representative sketch. So in most cases, what happens is the depth of the neutral axis is something like this. So the strain variation is something like this. So this value, let us call it, let us say epsilon cu. This value epsilon st. So epsilon cu is much less than epsilon st. Does that answer your question?
Yeah.
So in case of a homogeneous material, when let us say you have a steel block, in that case, you would have your neutral axis exactly at the center. And in that case, let us say this as epsilon compressive, or and let us call this epsilon t. In this case, your epsilon c would be equal to epsilon t if the material is homogeneous. But this is a heterogeneous material. Your neutral axis might be anywhere. It might be towards the top or towards the bottom, depending on what is the nature of the heterogeneity. Anyway, not getting into that. Anyway, if the maximum strain in concrete and the minimum strain in steel occur at the same time at the failure, then such a section is called as a balanced section. Okay. Now let us say that the reinforcement that we have placed in a balanced section is denoted by AST max. Let us just say, okay, that the reinforcement is denoted by AST max. Now the question is, what will happen if you provide reinforcement lesser than AST max, and what will happen if you provide reinforcement greater than AST max? To start with, if we provide reinforcement lesser than AST max, then the resultant section is called as an under reinforced section. Okay. Now, since we are providing reinforcement lesser than AST max, so let us try to understand it this way. There's a certain area. Let us say capital A, or let us say a max. Okay. Then now we are providing an area A. What is stress? Stress is equal to force upon area. So let us say this is F max. The stress value is F1. Then there's F2 is equal to F upon A. Now, which of these stresses would be greater? Will it be F1 or F2? A is less than M.
F2 will be
F2 would be greater than F1. Simple. So if we provide reinforcement lesser than AST max, what will happen is the steel will experience larger amount of stress and the steel will yield first. Okay, so let us try to put this in words. A section in which the area of tension steel is such that at the ultimate limit state, as the ultimate limit state is approached, the compressive strain in the extreme fiber of concrete is less than 0.0035, and the tensile strain in steel reaches the yield strain. And this particular section is termed as an under reinforced section. Now let us try to understand it with the help of a sketch. Just before that, the reinforcement in a balance section is denoted by AST max, and similarly, the depth of neutral axis is denoted by XU max. We'll understand why it is called max. Once we have understood these three types of sections. So this is XU max. The reinforcement is AST max, and the section is balance section. Now, okay. So what we are saying.
Bhagav, AST stands for area of the reinforcement.
Area of steel and tension. So steel is S, T is tension. Area of steel and tension.
Okay, thank you.
Okay. So what we are saying for an under reinforced section is, as the limit state of flexure is approached, the strain value here, that is epsilon st, has already reached this value, 0.002 plus 0.87 Fi by Es. But the strain in concrete, is less than 0.0035. Okay, so since we provided area of steel lesser than AST max, this steel experiences higher, because the force is not going to change, right? The force is the same. So this steel would experience larger amount of stress, larger amount of strain, and this value will reach first. So as the ultimate limit state is approached, this value is equal to 0.00. I would just make it in order to save space. Okay, anyways. So this value is 0.002 plus 0.87 Fi by Es. Okay. The question is, has the section failed? At this stage, has the section failed?
No, because EST is still at its lower limit. So I think steel
Okay.
can yield.
Okay, I think you're on the right track, but the answer could be, there could be a better answer. See, so firstly, when do we say that a section has failed? When the strain in concrete reaches 0.0035, that is when we say that the section has failed. Okay, so this is just a lower limit. If this limit is reached, we do not say that the section has failed. If the strain in concrete reaches 0.0035, we say that the section has failed. Okay, so just try to sort of write down the series of events. So the first series of event is epsilon st is equal to epsilon st star. Okay, but the section has not failed yet. The section has not failed. So of course we can go on increasing the load and increasing the resulting strain. So this is our stage number 1 that you see in red. When we load it further, the stress here would increase definitely, and the strain here would also increase because steel now has started yielding, so it can undergo a lot of strain. It might seem complicated at the start, but just stay with me here. Just hear out what I have to say, and perhaps then we'll develop a better understanding. So this is the blue line I would just separate this out a little bit. So I'm taking some time here. I just want to make sure that you understand this. So the first event is that epsilon st is equal to epsilon st star. So steel has started yielding. Let me just add this. Steel has started, okay, but section has not failed. Okay. What it means is that there is still further scope for increasing the load. So as we go on increasing the load, there will be a point when epsilon c will be equal to 0.0035. So this is our point where epsilon c has now reached 0.0035. Corresponding to this, the strain here is also going to increase. So epsilon st would be greater than epsilon st star. Now at this point, so EC or the strain in concrete is equal to 0. I would add this ECU, which is 0.0035, and then epsilon st is greater than epsilon st star, and now the section has failed, or we have reached our ultimate limit state. Now, if I compare the depth of my neutral axis with that of a balanced section, so this is the depth of neutral axis of a balanced section, and then this, if I look at the intersection of the blue line, I'll also make this blue. Okay, so this is the depth of neutral axis. Just give me a moment. Okay, so if I compare the depth of my neutral axis with the depth of neutral axis for a balanced section, what I observe is that the depth is lesser. So XU is lesser than XU max. Okay, so the bottom line is I can say that whenever my depth of neutral axis is lesser than XU max, the section is under reinforced section. Okay, we'll get into the details of it. We'll understand why and why this is important, or how does it simplify things. But right now, just stay with what we are trying to learn, and we'll keep on noting things, and we'll as we go on, as we get into the analysis, we'll understand why this is important. But just note down all the observations here. So here, AST provided is less than AST max. The depth of neutral axis XU is less than XU max. So that's how we recognize an under reinforced section. Okay, are there any questions here? Is it too technical to understand? So if it is, I just want you to honestly tell me so that we can sort of learn it using very simplified examples. Is it too technical to understand?
Can you explain it again? Like the second sentence.
Yes, I will explain it again. So what we'll do is we'll first look at an over reinforced section also. Okay, and then we'll see if overall we understand these three types of sections. Okay, and then we'll solve. If we try to sort of understand if there are still some gaps in some places. Okay, so this is about under reinforced section. Now let us try to understand an over reinforced section. So I'm just skipping this slide for the moment because we just want to look at what is an over reinforced section first. So a section in which the area of tension steel is such that at the ultimate limit state, the compressive strain in concrete, the compressive strain in extreme fiber of concrete reaches the ultimate strain, and the tensile strain in steel is less than the yield strain. It's termed an over reinforced section. So in this section, we are placing more reinforcement than AST max. Okay, greater reinforcement, lesser. This is just a way to understand it. Okay, greater reinforcement, lesser stress, lesser strain. Therefore, the strain here is less than epsilon st star, but this strain has reached epsilon cu. Let us try to understand this with the help of a sketch. So what we are saying here is at the ultimate limit state, this strain is equal to 0.0035, but this strain is lesser than epsilon st star. Now, if I join these two lines, let's reduce it further for ease of understanding. So when we reach the ultimate limit state, the strain here is 0.0035, but the strain here is less than epsilon st star. So theoretically, our section has already failed. The steel has not yielded. And if I compare the depth of neutral axis with that of XU max, what I observe is XU in this case is greater than XU max. Okay, so to summarize, if AST max is the area of steel for a balanced section, the resulting depth of neutral axis is XU max. If AST is less than AST max, the depth of neutral axis XU is less than XU max, and the section is called as under reinforced section. If the provided reinforcement is more than AST max, the depth of neutral axis is greater than XU max, and the resulting section is called as an over reinforced section. So what is the difference between an under reinforced section and over reinforced section? In an under reinforced section, the steel has started yielding, meaning that we get a lot of or we get a lot of warnings before the beam actually collapses. The steel yields, and therefore whenever this point occurs, the steel has already yielded. Therefore, it can the beam as an element can deflect a lot. There, we could see a lot of cracking. Therefore, we can say that this beam is going to collapse. So we get a lot of warning before this section actually fails because the steel has yielded. On the other hand, in an over-reinforced section, since the steel does not yield at all at failure, the failure is very brittle or the failure is very sudden, and therefore, before a physical collapse, we do not get a lot of warning in an over-reinforced section. So this is the fundamental difference between under-reinforced and over-reinforced. So now the question is, which type of section are we desiring? Should we look for designing sections as an under reinforced sections or over reinforced sections?
Under
Under reinforced, so for obvious reasons that we want the failure to be ductile, we want enough warning before the beam actually collapses, and therefore we want an under reinforced section. And reason number two, unnecessarily we don't want to provide more reinforcement, thereby increasing the cost of the beam and thereby increasing the cost of the structure. Two simple reasons. Okay, so now I would just explain the under reinforced section once again to ensure that we are sort of not leaving any gaps in terms of, because everything that we learn here onwards is based on these fundamentals. So I just want you to pay attention and try to understand it one more time. If there are still any gaps, we'll work on it again. So in an under reinforced section, as we are moving towards the ultimate limit state, or as we are moving towards failure, what happens is, before that, just a moment. Yeah. What happens is the strain in steel reaches the value of epsilon ST star. But at the same time, the strain in concrete is less than 0.0035. So we have two limits, limit 1 on concrete, limit 2 on steel. So the lower limit of steel is already hit, okay? But the upper limit of concrete is not yet hit. Our failure criteria is very clear. When this value reaches 0.0035, the beam has failed. Very clear criteria. So at point 1, the beam has not failed yet, which means that we can increase our loading on that beam. Okay, when we load it further, the strains are going to increase. The strain which was here, then we'll have a strain value here, then here, then here. At point number 2, what happens is now the strain in concrete hits 0.0035. Similarly, the strain in steel is also going to increase because steel has now yielded. So at point 2, we reach a value of epsilon ST that is greater than epsilon ST star. Now, what is that value? We don't care, because all we cared about was this value. We don't care about what this value is. So at point 2, our epsilon C is equal to epsilon CU, which is equal to 0.0035, and our epsilon ST is greater than epsilon ST star, and the section has failed in a tiled manner. I would just add here that the section has failed in a little. So this is the difference between a balanced section, an under reinforced section, and an over reinforced section. Questions?
Bhargav, so then when you're designing a beam,
Yeah.
in many ways, like you're looking at an under reinforced section, but then to design beam so that it would work, the neutral axis of that beam should be between the neutral axis of the balanced section and the under reinforced section, right?
Okay. So I sort of understand what you're trying to ask. Okay. Let me see if I can answer this. So if the neutral axis here is here, it is an under reinforced section. If the neutral axis is here, it's an under reinforced section. Or if the neutral axis is here, it is still an under reinforced section. Okay. So AST max is a singular number, but anything lesser than AST max is not a singular number. So any section that has reinforcement lesser than AST max is an under reinforced section. So our only benchmark is AST max or XU max. Anything less than that is an under reinforced section. So this number is not fixed. So I think what your question was is, so just to make sure that the beam would work, our neutral axis should be somewhere in between. No, it
Yeah.
does not mean that. What it means is your neutral axis should be anything less than XU max.
Okay.
This XU is not fixed. XU max is fixed. XU is not fixed. So we are targeting anything that is less than XU, anything in this zone.
Yeah.
Okay. Any more questions? Now I would go back to a couple of slides that I skipped. So in an under reinforced section, the area of steel provided is less than AST max. Failure initiates by yielding of steel, and hence it is termed as tension failure. This kind of a failure gives ample warning of the impending collapse. This is highly preferred in design practice because we do not want any failure to be sudden. Every failure, if at all it occurs, has to be ductile. Okay, so though the failure initiates by yielding of steel, the actual collapse occurs by eventual crushing of concrete. So in an under reinforced section, we cannot say that it's a failure because of steel. The ultimate failure is going to occur by crushing of concrete because that's a failure criteria. So let us just try to see experimentally what happens in an under reinforced section. Okay, perhaps this would make our concepts clearer. Just a moment. I think I'll have to share the system volume as well.
This video shows an under-reinforced concrete beam being tested in bending. The specimen is made from concrete containing regular Portland cement. The rebar is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point bending. The testing rig is now starting to apply vertical loads to the specimen, and we can see that it is deflecting and starting to crack. This means that the steel in the beam is taking up the tension that is developing in the lower half of the section. So if we take a closer look now, we can see the cracks opening up as the steel takes the tension. The steel starts to yield, which allows the beam to deflect greatly, and eventually the beam fails. The graph initially shows a linear relationship between applied load and vertical displacement at mid-span. This is the elastic loading zone. But then the graph plateaus, which corresponds to the point at which the steel begins to yield. Note that failure is gradual rather than sudden. This is because failure is due to the steel yielding, which is a ductile process, and very distinctive of an under-reinforced concrete beam.
Okay, so what I want us to note is this. Just give me a moment. Okay? I think I'm not getting control.
This video shows an under-reinforced concrete beam being tested in bending. The specimen is made from concrete containing regular Portland cement. The rebar is regular reinforcing steel.
Just give me a moment, okay? I just want us to focus on a particular
In the lower half, we can see the cracks opening up as the steel takes the tension.
So this is our state number 1, wherein the strain in steel has reached epsilon st star, but the strain in concrete is still less than 0.0035. And therefore we start seeing cracks here, which is an indicative of the steel has started yielding now, because of which we are sort of seeing these cracks. So we have reached state number 1.
The steel starts to yield, which allows the beam to deflect greatly.
See, there's so much deflection in the beam, it's visible, but still the concrete is not crushed, or the strain in concrete is still less than 0.0035.
And eventually the beam fails.
And now this is our state number 2, wherein the strain here has reached 0.0035, and the strain here is greater than epsilon st star. This is our under reinforced section. Now let us also look at the over reinforced section.
This video shows an over-reinforced concrete beam being tested in bending. The specimen is made from concrete containing regular Portland cement. The rebar is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point bending. The testing rig is now starting to apply vertical loads to the specimen. We can see the beam displacing and cracks opening up on the tension side of the beam as expected. Then all of a sudden, the concrete in the top surface of the beam fails explosively. Right, let's slow down the footage. Let's look at the top surface. Remember that the top side of the beam is under compression. Because we have heavily reinforced the lower part of the beam, which allows a large amount of tension to be carried, the same large amount of compression needs to be carried by the concrete near the top. This causes the concrete to crush before the steel has a chance to yield. Now, for a structural engineer, that's a bad way for a beam to fail, because concrete crushing is brittle, it's sudden, and you don't get the gradual failure that you'd obtain in an under-reinforced beam. The graph shows an initial linear relationship between the applied load and the vertical displacement at midspan. Note that there is no plateauing in this plot because the steel doesn't yield. Instead, the rising plot simply stops, which implies a sudden failure, just as we saw in the video. The beam is under compression before the steel has a chance to yield the top.
Okay, so I just wanted us to focus here. Here, we don't have stage 1 and stage 2. That's we directly have an end stage here. So the steel is not yielded yet, and the maximum strain in concrete has reached a value of 0.0035, which means that the concrete has crushed, but the steel has not yielded, because of which we don't see nicely distributed cracks here. We don't see a lot of deflection, and there's a sudden or an explosive failure. And such a kind of failure is not desired. So again, a slide that is skipped. Section is. So this failure is sudden by crushing of concrete, and hence it is termed as a compression failure. This gives almost no warning before collapse, and it is not preferred in design practice. So this is the difference between a balanced, an under reinforced, and an over reinforced section. Questions?
I have a question. So is there any lower limit for under reinforced sections? Because if it's just under reinforced,
Lower limit what?
pardon?
Lower limit for what?
Like if the neutral axis was too high on this graph, wouldn't it fail immediately with the slightest? Wouldn't it like start deforming with the slightest load?
That is correct. But okay, I sort of understand what you're trying to say. So I think what she's trying to say is there a lower limit for XU max, for XU, for example, if the failure is occurring for, just give me a moment. First, let me know if I read your question correctly. What you're saying is there any lower limit for XU? Because what this could mean is if the XU is much smaller, what this could mean is we'll have a failure strain distribution, something like this.
Yes, that's what I was asking.
Okay, so our objective is whatever is the depth of the section, the depth of the section has to be optimal. Okay, meaning that we are sort of aspiring for a balanced section. So we are sort of aspiring for this situation, but we don't reach here. This is our, what I would say is this is our maximum limit. So what we are trying to do is we are trying to get as close to XU max, but not to XU max, because after that we're just sort of at the edge. So our objective is we are trying to get as close as possible to XU max. So there's no lower limit. If perhaps your depth of neutral axis looks something like this, it means that you have given a very deep section, which is not even required. And in design practice, you will not see examples as such, because what it would mean is that you have given a very deep beam than what is required. So you will not encounter, in design practice, you will not encounter an example like this. So this XU max is an optimal case, and we are just trying to be as close as possible to the optimal design. We are totally avoiding to be in this region, and we are sort of targeting to be as close to XU max as possible. And therefore there is no limit, there's no lower limit to XU. You can sort of design a section in such a way that it gives a very low value of XU. It's not a design limit, but that would not make any sense design wise.
Thank you.
Any more questions? Have everyone understood everything? Okay, just to get a consensus, how much percentage of this have you understood? 10%, 15%, 95%, anything. See, if you don't give me a feedback, there's no way for me to know ki samjha hai ki nahi, should I go ahead or not.
After revising, it will be around 80, 90. It's
Okay.
just, I'm just, personally, I'm feeling a bit out of it. So I think I'll just have to watch the lecture over and over again, like
Okay.
over at least once. Because I'm a bit sleep deprived right now, actually.
Okay, what about others?
Yeah, I think 90.
Yeah, it's understood, and maybe with the revision we can.
Okay. Some people have not spoken yet. How much have you understood?
Need to go through the lecture once again to like get it fully.
Okay, no problem. But I understand that this is very new. This is the first time we are learning the design of reinforced concrete elements. So if at all there are any questions, a good time to ask would be next lecture, rather than looking at it only before the exam and then having a lot of questions. So give it some time, give it a revision, and then if there are any questions, we'll look into it. So this was the basic theory behind analyzing or designing flexural members. But yet this is just a theory now. We still do not have any equations, or we have not still looked at any numbers. Okay, this is okay, but how to size a beam, how to provide reinforcement a beam, this is not something we've learned. So this we'll learn in the next part of this chapter, which is the actual analysis of singly reinforced rectangular sections. Now, what we are going to do is we are going to analyze a beam. We are like, I think our scope, we are limiting our scope to analysis of beam. We are not going into the design of beams. We are not going to get into the design of singly reinforced or design of reinforced rectangular sections. We are going to look at the analysis, and I'm going to give you the thumb rules for sizing beams. So you'll understand that if your span is such, and if your end conditions are such, then you can, sort of use any thumb rule. For example, let us say L by 15 for a particular condition. It might be L by 20 for a particular condition, and that would help you size those beams. Okay, that's very basic. But in terms of placing reinforcement, we are going to get into the analysis. We are not going to get into the design. So now the question is, what is the difference between analysis and design? So in analysis, you have all the information about the section. You have the width, the depth, the reinforcement provided, the grades of steel and concrete, and then you just have to find out if you also have the loading. You just have to find out if the section is adequate or not. That is called as analysis. In design, you have only loading. You don't have anything else. You have to decide. If it's a theoretical, if it's an exam question, you'll also have the grade of concrete and grade of steel. But then you have to decide what is the width, what should be the width of the beam, what should be the depth of the beam, what should be the reinforcement quantity. Okay. Now I'm deliberately not getting into the design because that is something that you are not going to actually do. In your in your profession, what you're also not going to analyze, and there's no debate on that. But this is a basic, like, as as an architect, if you just look at the section and see the reinforcement provided, you should be able to understand if there's any further scope for reducing the depth of the beam, or you feel that the beam is heavily reinforced and there's definitely some scope of reducing it. That is the reason I think we should look at analysis at least, if not, the actual design. So our focus is going to be on the analysis. I'm repeating this again. Analysis means you have all the section information, you have all the loading information. You just have to find out if the provided section works or it does not work. It's that easy. Okay, so we'll just take a short break of 5 minutes. At 11, get your pens and papers. we are going to get into numbers. We are going to come up with a analysis procedure, and then we'll solve a couple of examples. Okay. So in the meantime, if you have any questions, I am available. Okay, please write down. Analysis of singly reinforced rectangular sections. Analysis of singly reinforced rectangular sections. Consider a rectangular section. Consider a rectangular section of width B and total depth capital D. Of width small b and depth capital D. Reinforced with total area of reinforcement AST, reinforced with total area of steel or total area of reinforcement AST only on the tension side. Only on the tension side. Such a section is often called as singly reinforced section. Such a section is often called as singly reinforced section. The depth small d, the depth small d of the centroid of the tension reinforcement below the compression phase is called as effective depth of the section. What it means is the distance of the centroid of the tension steel from this phase, which is capital D. This is the effective depth. If you've noticed, we have been drawing all our strain diagrams only up to the reinforcement centroid.
Excuse me,
Yeah.
Bhargav, are you sharing your screen?
Yes, I am.
We
No, I'm
can't
not.
see.
No, we can't see it.
Okay. So we have been drawing all our strain diagrams only up to the centroid of the reinforcement. We are not drawing our diagrams up to the lower soffit of the beam. Can someone answer why?
Because when they talk about tension, the load of the tension is mainly sent to the taken by the reinforcements, not the concrete mass.
Because we are ignoring the concrete in tension. Therefore, it is not going to help us in any way by drawing this diagram up to here. Though it is valid till there, but we are interested only up to this point. We are basically
We've assumed it to be zero, right? Since it's
yes,
negligible.
we are just assuming that there is. If I say this is a neutral axis, we are just assuming that there is no concrete in this zone. So it does not, and that's the reason why we are interested in the effective depth. We are not interested in the total depth. We are interested in the distance between the centroid of the reinforcement to the compression phase. So capital small d is more important to us than capital D. Okay, I just want you to draw this sketch and leave out some space on the right side here. We are going to add more diagrams here. So just draw this sketch. Done? So now let us sort of try to describe what we see here. So epsilon st is the strain, before that, epsilon cu is the strain in concrete at ultimate limit state. So this is a theoretical failure state. Epsilon st is the strain in steel at ultimate limit state, and xu is the depth of neutral axis. Okay, I'm just assuming that you're noting this down, simultaneously. If you think that's too fast, let me know. We'll slow down a little bit.
Can you slow down a little bit?
Yes. Or what we could do is we could just go through the explanation first, and then you could write it down later. Okay. So towards the end, I'll just give you some time to write this down. But it's very important that you write this down, because then you just actually get a feel of the process of developing these equations. So I strongly suggest that you write this down.
So
So
once
just,
you understand, it's just we just copy what's on the slide once you've understood it, right?
yes. Okay. So this is a strain in steel, this is a strain in concrete, this is the depth of neutral axis. Now the question is, why have I not written epsilon st is equal to epsilon st star and so on? Because this is a failure. Okay, there's no real definition of what epsilon st should be at failure. We're just talking about epsilon c is equal to 0.003. That's it. So now I have to find out, at this particular state, what is the strain here. So if I consider similar triangles, if I consider this as triangle 1, triangle 2, I hope all of us know what similar triangles are. So considering these are similar triangles, this depth, which is xu, upon this depth, which is d minus xu. If there's any confusion, I'll also point this depth. So this depth is equal to d minus xu. So this is xu, this is d minus xu. So xu upon d minus xu, I can write this as xu upon d minus xu is equal to epsilon cu upon epsilon st. That's what I've done here. So xu upon d minus xu is equal to epsilon cu upon epsilon st. Therefore, epsilon st is equal to, we've just rearranged this. Epsilon st I take to the left hand side. So this is equal to d minus xu upon xu into epsilon cu. So if we know, so basically using this equation, we can find out what is the strain in steel at failure. Epsilon cu, we already know it is 0.0035. Xu, we learn to find out. The basic objective is we can find out what is the strain in steel at failure. Okay. Next, let us try to find out what is the limiting depth of neutral axis, or what is the maximum depth of neutral axis. Now, for a balanced section, we know that this value is 0.0035 and this value is 0.002 plus 0.87 Fy upon ES. Using this information and using this equation here, I just highlighted. Using this equation here, we can find out what is the value of xu. Okay. Now, again, by considering similar triangles in the strain diagram, I can write xu upon the total depth. So xu upon the total depth is equal to cu upon cu plus epsilon st. Talking about this equation here. Is there any difficulty understanding this equation? What I've done here is xu upon the total depth is equal to, what is the strain corresponding to xu? Epsilon cu. And what is the strain corresponding to the total depth? Epsilon cu plus epsilon st. If you find this difficult, you could also stick to the original equation and write xu 2 times. You could also stick to this equation. Some quick feedback. Are you understanding this? Do you want me to repeat it?
Yeah, I did not understand the ECU plus EST part.
Okay. So let us, what we'll do is we'll write our original equation. Just give me a moment. So anyway, we are not writing anything right now. So XU upon D minus XU is equal to epsilon Cu upon epsilon St. This is our original equation. If I rearrange this, so Xu into epsilon St is equal to D into epsilon Cu minus D into, Xu into epsilon Cu. So if I rearrange this again, so Xu would be equal to D times epsilon Cu upon epsilon St plus epsilon Cu. Okay. So what we'll do is, we'll start, at least you have understood the equation on the left, right?
Yeah.
This equation, okay. So I'll just start with that equation. Xu upon D minus Xu max, write it this way, is equal to epsilon Cu upon epsilon. It's a basic equation. Now we'll just have to rearrange this. So Xu max into epsilon St so this is equal to epsilon Cu into D minus Xu max. So if I again rearrange this, what I'll get is Cu into Xu max. Just multiplied epsilon Cu inside to both the equations. If I rearrange this further, what I'll get is so what I did is I just shifted this term from RHS to LHS. So Xu max epsilon St, then this shifted this term on the right. I'll take Xu max as common and rearrange this. Xu max. So this Xu max is equal to this upon So I just took out XU max common here, and then we get epsilon ST plus epsilon CU, which goes to the denominator, and this is epsilon CU into D. So this is the final equation that we get. Okay, which we could have got even considering the similar triangles, but just for the ease of explanation. So XU max is equal to epsilon CU D upon epsilon ST and epsilon CU. It's not something you have to remember. We're just getting to something that is important to us using this process. So finally, if I have to rewrite this, just give me a moment. Huh? If I just have to write this in terms of D, so all the distance terms on the left hand side, all the strain terms on the right hand side. I can also write it like this. So this is the equation that I had started this derivation with. XU max upon D is equal to epsilon CU upon epsilon ST plus epsilon CU. Very simple. Now we already know these values. So epsilon CU is 0.0035. Okay. Not change anything, okay? Just is their order. So this is equal to 0.0035. This is again 0.0035. For a balanced section, epsilon ST is equal to epsilon ST star. Therefore, I have written 0.002 plus 0.87 Fi upon ES. So now I have got an equation for XU max in terms of D. So if I look at this equation, there's only one variable, and that is Fy. There's no other variable. ES remains same irrespective of the grade of steel. So there's only one variable. So I hope you know what are the commonly used grades of reinforcing steel. So the most commonly used is Fe 500. The ones that were used in the past are Fe 250, then Fe 415, then we have Fe 500 and Fe 550. We look at them, okay? So if I say Fe 250, meaning that Fy value is 250 megapascal. So I can rewrite this equation as XU max upon D is equal to 0.0035 plus 0.0035 plus this entire thing with Fy as 250 megapascal and Es as 2 into 10 power 5 megapascals. If I solve this equation, I get a value of 0.53. So for Fe 250, XU max is 0.53 times D. If I substitute the value of Fy as 415 megapascals, so I just substitute 415 here, I get a value of XU max is equal to 0.48 times D. Now, if I substitute the value for Fe 500, which is 500 megapascal, I get a value of 0.46 times D. And if I substitute a value for 550 megapascal, just substitute 550 here, I get a value of XU max is equal to 0.44 times of D. Now, why am I throwing all these numbers at you? What I want to highlight is that irrespective of the grade of concrete, the width of the concrete section, or the amount of reinforcement you have put in, irrespective of all that, your XU max depends only on the effective depth of the section and nothing else, and the grade of steel. So for Fe 500, irrespective of the amount of steel you put in, XU max is only a function of its depth. For Fe 415, XU max is always equal to 0.48 D. For Fe 500, XU max is always equal to 0.46 D. For Fe 550, XU max is always equal to 0.44 D. How does that help us? That helps us in deciding if a section is under reinforced or over reinforced, because we have seen that if XU is less than XU max, the section is under reinforced. Now, how can we get the value of XU max? For that, we don't need anything. The only thing that we need is what is the grade of steel and what is the depth of the section. That's it. Using this, we can obtain the value of XU max, and then we can just find out what our XU is, compare these two, and say if a section is under reinforced section or a section is over reinforced section. So what we are trying to do here is we are just calculating the value of XU max. So XU max is our benchmark. Referring this benchmark, we can define our section as under reinforced and over reinforced. And what we've just learned is that it's very easy to find out this value. It depends on only two things. One is the grade of steel, and another is the depth of the section, particularly the effective depth of the section. It is a function of only these two things. So if we know this, we can easily find out what is the value of XU max. Once we have this, we can compare our XU with XU max and say and section is under reinforced or reinforced balanced. That's the objective. Any questions here? Have you guys understood everything? So there must be some questions.
I think when we look at the class again, then we might have some questions, but right now it's clear.
Okay, if it's clear, then well and good. See, the reason for directly, if this is too much confusion, if you see अरे इतना सारा terms है, ये बहुत confusing है. It's very simple. You don't even have to do this. See, just यहाँ पे इस triangle को देखो. If once, okay, how do I put it? It's very simple. So let us say two similar triangles, side 1 upon side 2 is equal to so what I can call it, okay, rather than this. Similar triangles here. If let us say that this triangle is A, this triangle is B, let us say that this side is 1, this side is 2. So naturally, this side is 1 and this side is 2. Okay, so A1 upon B1 is equal to A2 upon B2. I hope everybody understands this. So I can also write this as, ये पता चला ना, I'm calling this side as A1. So this is triangle A का first side. So this side is A1. So A1 upon B1 is equal to A2 upon B2. Okay, junior, this is junior KG stuff. So I've just written this as A1 upon B1 is equal to A1 plus B1. Okay. और थोड़ा सिंप्लीफाई कर देते हैं. Just a moment. So I can also write this as A1 upon A1 plus B1 is equal to A2 upon A2 plus B2. This is all I've written here. So my A1 is XU max. XU max upon the total depth is D, which is A1 plus B1. This is D. Is equal to A2, which is epsilon CU upon A2 plus B2. So 0.0035 plus epsilon C star. So अगर ये आपको बहुत confusing लग रहा है, तो इसको जाने दो, सीधा ये equation पे आओ. See, I'm asking you to skip this because this is not the intent of this discussion. This is just a mathematical procedure. I don't want you to blindly, tell you that XU max is equal to 0.53D without telling you that how I've come to this number. That's the only intent. Okay, I think we already exceeded our time. So I just want you to give some time to go about these equations that we have seen today. ask me a lot of questions in the next lecture, and just ensure that we are on the same page before we go ahead. So if you want to write all this down, please go ahead. I'll keep sharing the screen. Whenever you want to go to the next page, you let me know. Or what I could do is, so both the pages are in place. Please write this down. Give it some time. Go through the lecture if required, but definitely go through the notes. We'll continue this in the next lecture, and let me know if you have any questions. And today we unfortunately do not have enough time for the quiz, and I think this was more important than a quiz. So next lecture we'll definitely have a quiz, and that's it from my side. Let me know if right now also you have any questions. Let me know. I'm here for some time.
Will you be adding today's questions to the next test as well, or will that be for the first two classes?
No, up to here, whatever we have learned up to here, up to this point.
Okay, for next time. Got it. Thank you.
Yes.
Thank you.
Thank you.
Thank you.